Ladies and gentlemen, it is my great privilege on this occasion to present Edward Witten for his plenary address, String Theory and Geometry. As you may have noticed, the program of this Congress, the Berkeley Mathematical Congress of 1986, differs from its predecessors in the much greater emphasis given to the relationship of mathematics to the sciences, both natural and artificial, to physics and to computer science. This is true particularly of the plenary addresses, but also of the remainder of the program. And it reflects, in my view, a profound change which has taken place in the structure of mathematics at its cutting edge, what has been described by some of my acquaintances as a profound reconvergence of mathematics with the sciences. Edward Witten epitomizes this tendency in his sharpest form. By training and profession, he is a physicist. He is a professor in the Department of Physics at Princeton. And by achievement, he is a physicist at the highest level and a mathematician at the highest level. He has been one of the leading workers in recent years in the ongoing development of string theory. He has been one of the, perhaps the leader in introducing ideas of conceptual originality and mathematical sophistication in that theory. And he has also used those ideas in a very remarkable way to get important mathematical results of a high degree of originality, both in concept and execution. In their lectures, both Richard Schoen and Izzy Singer have referred to some of these results. Another one to which they have not referred is his highly original proof of the Morse inequalities using the eigenvalues of Laplacians on manifolds, the first original proof of that set of ideas in 50 years. The material of which he's going to speak reflects one of the most powerful trends in contemporary mathematics and the most powerful and sometimes controversial trend in theoretical physics. The development of fundamental ideas concerning the unity of the theory of fundamental particles and of gravitation in a highly sophisticated and elaborated mathematical form. We welcome him here as a symbol of this movement, which will continue, I am sure, in even sharper forms in the decades to come. Professor Witten.
In 20th century physics, there have been two really basic ingredients, which are first of all general relativity, which is Einstein's theory of gravity, and secondly quantum field theory, which is the basic framework for our understanding of essentially everything else in physics other than gravitation. Though they both play a role in a description of the same natural world, these two theories enjoy their successes in very different realms. General relativity has its successes in the realm of astronomy, and quantum field theory is the framework for successful descriptions of many aspects of the properties of atoms, molecules, and subatomic particles. Most of the really important developments in fundamental physics since about 1930 have been developments in quantum field theory, or certainly in quantum mechanics. And for much of this time, physics and mathematics had relatively little interaction compared to that in many previous epochs. One obvious reason for this perhaps, is that in the 20th century, mathematics advanced into seemingly abstract realms, unrelated, perhaps it would seem, to the humdrum world of the theoretical physicist. But I think in large part the reason that the interaction of mathematics and physics was more limited in the last half-century than in previous epochs was because the physical problems that arose in quantum field theory, which was the central framework for most progress in physics, did not seem to give rise to many interesting mathematical structures. By the mid-1970s, this changed mainly because of developments in physics. By the mid-1970s, the quantum field theories which had emerged to play a central role in physics were the so-called non-abelian gauge theories, theories in which one of the main ingredients is a vector bundle over space-time with a non-abelian structure group. These theories raised more interesting and significant issues in geometry and topology, causing a more significant interaction of physics and geometry, starting about 10 years ago perhaps, than had been possible during most of the epoch in which quantum field theory played its central role in physics. In fact, one of many strands leading to Donaldson's work, which we heard about a couple of days ago, originated from this interaction of physics and geometry. Now, progress in quantum field theory led by perhaps a decade ago to the beginning of an enriched interaction of physics and geometry. But I believe that all the same this interaction would remain relatively limited if it were only a question of quantum field theory. It's really in trying to go beyond the limits of quantum field theory that physicists have come upon mathematical frontiers. Perhaps the fundamental limitation of quantum field theory is the one I've already alluded to. It's only one of two fundamental theories in physics, and in fact, quantum field theory turns out to be incompatible with that other basic ingredient in 20th century physics, which is general relativity. You can attempt formally to combine these two theories by so-called quantization of general relativity, but this leads to all kinds of nonsensical formulas. Now, in the early days of quantum field theory, it was not at all obvious that this was a central problem. Quantum field theory faced many problems in its early days. It wasn't even obvious at the outset that the quantum field theory of electricity, which was the original quantum field theory, really made any sense. In time, though, the other difficulties of quantum field theory were overcome, and it became clear that quantum field theory was an adequate framework for describing all of the forces of nature except gravity, though in the course of learning how to do so, physicists were led to develop quantum field theories with a richer geometrical content, such as the non-abelian gauge theories I alluded to previously. As the other difficulties of quantum field theory were overcome, the incompatibility with general relativity emerged as the limitation of this framework. Now, general relativity is based, of course, on Riemannian geometry, which is certainly one of the richest frameworks for our understanding of ordinary geometry. And asserting that general relativity, which is based on Riemannian geometry, is incompatible with quantum field theory must mean that some proper physical theory which will successfully generalize general relativity and reconcile it with quantum field theory must in some way be based on some generalization of Riemannian geometry compatible with the requirement of quantum mechanics. Now, experiment can only provide us with indirect clues about how we should go beyond ordinary Riemannian geometry as a framework in physics. And the reason for this is that, to our great regret, gravitational effects are unmeasurably small in experiments that probe quantum field theory, and the same is true the other way around. There is actually only one example in the previous history of physics in which a theory was invented even though the experimental clues were only indirect. The one other success of that nature was general relativity itself. It was discovered in what we might call a logical way. Einstein first, beginning only with a very general clue, which was that special relativity was incompatible with gravity. Einstein first formulated the physical ideas for reconciling two inconsistent theories, then found the right mathematical framework, which was general Riemannian geometry, and finally he invented the theory. Now, of course, we'd like to emulate this history, but that is easily said than done. Many ambitious physicists and mathematicians have gone off into the wilderness in search of some fundamental generalization of geometry that would reconcile gravity with quantum mechanics. But generally speaking, they've come back empty-handed, if at all. While direct assaults on this problem have yielded little, progress seems to have fallen from the sky, essentially, through the largely chance discovery of something called string theory. Now, the people who invented string theory beginning in the late 1960s weren't aspiring to reconcile general relativity with quantum mechanics. They weren't hoping to generalize Riemannian geometry. In fact, the ambitions were not in the realm of our discussion at all. String theory was originally developed as a theory of the so-called strong interactions, the nuclear forces that keep nuclei together despite the electric repulsion among protons. Even as a theory of strong interactions, string theory was discovered largely by accident. Following its discovery, which essentially occurred when one of the formulas in string theory was written down by Veneziano with very slender motivation in 1968. Following the essentially accidental discovery, it was vigorously developed in this early period, during which upwards of 500 papers were written, led to an extremely rich mathematical structure, which fascinated people by its richness, yet never advanced towards solving the original problem which motivated this work of strong interactions. And in fact, this whole line of development was abruptly abandoned by most physicists around 1974, when it became clear that it was not the correct approach to strong interactions. While it was generally abandoned because of not being the solution of the original physical problem, the structure retained its fascination, provoking work in various areas, and eventually being revived in the 1980s as an approach to quantum gravity. Now, this subject has already an extremely long and complex history, and I fear that if I tried to survey even the high points of this history, it would take the rest of the lecture. I've written here some of the dates and names of some of the main developments, but it would be impractical to explain even a few of them completely. I'll be talking about some ingredients from some of these developments, but I'm not going to attempt to explain this history. Now, as I've indicated, string theory essentially fell from the sky by chance, with some special formulas of this theory being discovered with a rather strange motivation, and it gradually being learned that these formulas were special cases of a richer structure, in which one has penetrated in time to deeper levels, but probably not very far toward the deepest levels that underlie this theory. The situation in string theory is roughly as if Riemannian geometry had been, it's roughly as if general relativity had been invented without having first invented the logical framework for this theory, which is Riemannian geometry. Einstein happens to have followed Riemann, but it's imaginable to have conceived of a planet where the problem that Einstein posed of reconciling gravity with special relativity would have existed on a planet where general relativity was unknown. Conceivably, on such a planet, general relativity would somehow be invented in some obscure way without its logical underpinnings, Riemannian geometry being clear. Whether or not that's happened on some planets in the universe in which theoretical physics may have been developed, it certainly has happened on planet Earth in the case of string theory. Because of the peculiar way that string theory has been discovered, I cannot do what I would dearly love to do, and what I hope will be done by some speaker at some future Congress of the International Congress of Mathematicians, which is to explain the basic concepts of curvature, connections, and Riemannian manifolds, which should play in string theory the role that Riemannian geometry plays in general relativity. I can try to explain some of what presumably are the preliminaries for this theory. And in sketching what I mean by these preliminaries, perhaps I'll give you an analogy with general relativity. In Riemannian geometry, one has some curved manifold. And if you consider at a point the tangent space to this curved manifold, of course the tangent space is a linear space. And one thing you certainly have to be able to do in order to work with Riemannian geometry is to understand a little bit of elementary linear algebra so that you can carry out linear operations in the tangent space. Roughly speaking, our present understanding of string theory was as if we were trapped in the tangent space of a Riemannian manifold, not understanding the basic frameworks that we would need, the basic logical concepts that we would need to go coherently beyond linear operations in the tangent space. So the analog in string theory, the role which is played by linear algebra as a preliminary to work in the tangent space of a Riemannian manifold, that role, the analogous role, is played in string theory by much richer mathematical structures, which are the theory of Riemann surfaces, modular forms, and what I will loosely describe as infinite dimensional representation theory. Roughly speaking, just as one needs a little linear algebra before trying to learn Riemannian geometry, so one needs to know something about Riemann surfaces and infinite dimensional representation theory before trying to learn string theory. So we could say that general relativity requires linear algebra for its linear approximation, but the fundamental ideas in the theory are really connections, curvature, and Riemannian geometry. String theory requires Riemann surfaces and infinite dimensional representation theory for its linear approximation. And what should really belong in the lower right-hand corner of that square is, I think, to my thinking and the thinking of many other physicists, really the central problem in theoretical physics. Now, I've stressed the incompatibility of quantum field theory with gravity, but in fact, there are certain other problems in our understanding of physics that we would like to overcome. And one of the most fundamental problems is simply that there are too many conceivable theories permitted by the general principles that we have. Quantum field theory would permit an infinity of theories, and the logical framework of general relativity would also permit an infinity of theories, of which Einstein's is only the prototype. Of course, if you try combining these two frameworks, you have not an infinity of theories, but zero, which is the assertion that they're incompatible. But if you could have combined quantum field theory with general relativity with no particular difficulties, then you actually would have had an infinity of possible descriptions of the natural world, which certainly would mean some basic gaps in your understanding. So in a sense, there might be a blessing in disguise in the difficulty of reconciling these two frameworks. Either would separately permit an infinity of theories, together they seem to permit none, and hopefully the proper understanding will lead to a finite set of theories that reconcile them. To briefly illustrate what I mean in saying that the general ideas of Riemannian geometry would permit an infinity of theories, the basic concept in general relativity is really that space-time, which I'll call M, is a pseudo-Riemannian manifold. It has a metric tensor G, and Riemann tensor, the Ricci scalar, is what I've called R. Einstein's basic principle was to describe nature by some geometrical action principle. Some geometrical integral over space-time was to be the action of this theory. And while he wrote the simplest action, there are an infinity of more general action principles, more general geometrical invariants integrated over M that would give conceivable generalizations of general relativity within the logical framework. In some sense, you might consider this to be the most elementary member of the clan, but when you consider another point which I'm about to allude to presently, in fact, one has an infinity of theories without an evident most elementary example. So apart from the inconsistency of quantum field theory and general relativity, we would certainly like to overcome the fact that either of those separately leave us with too many theories, in fact with an infinity of conceivable theories. illustrate the other deficiency of general relativity, let me briefly discuss almost flat solutions of this theory. Of course, in everyday life, we don't notice that space-time is curved. Space-time is flat in everyday life, and of course you can do a better job of probing for curvature if you measure over larger and larger scales. Every Riemannian manifold is almost flat on a small scale. Gauss, as many of you know, measured the angles between three high mountains and found pi as the sum, confirming that on the scale of the Alps, space-time is roughly flat. And astronomers do much better on even larger scales. So we introduce as a good approximate description the flat metric eta, the diagonal metric with these eigenvalues. And we imagine a small deviation h from a flat metric. We write the space-time metric as the Minkowski metric plus a small fluctuation. Well, if we insert this form of the metric in the Einstein equations, we'll get a nonlinear equation. But since space-time is nearly flat, let's linearize it. If we linearize it, we will get some linear equation for h, which will be some perturbation of the Laplace operator acting on h, giving 0. Well, this equation has wave-like solutions, the simplest being the plane wave I've written here. And these wave-like solutions are quite analogous to the corresponding wave-like solutions of Maxwell's equations, which are light waves. So in this way, we learn that general relativity predicts gravitational waves. A prediction of that theory which emerged clearly when the theory was formulated in 1915, though it had been conjectured by Poincaré some 10 years earlier. And incidentally, a prediction which was finally tested indirectly by observations of radio waves from pulsars just a few years ago. Now, when this prediction was made, it was a prediction of a new type of wave, not a new type of particle. But in fact, in quantum mechanics, waves and particles are two facets of the same thing. So this prediction of a new kind of wave is actually a prediction of a new kind of particle. Einstein merely aspired to reconcile gravitational forces with special relativity, but in trying to do so, he actually predicted a unified, not just a theory of gravitational forces, but a unified theory of gravity and matter. Gravitational forces were unified with this peculiar new kind of matter which was predicted, namely gravitational waves. Now, Einstein wasn't satisfied with this unification, since he eventually hoped to unify gravitational forces not with some exotic form of matter that he predicted, but unknown at the time, but with the forms of matter that were known about. So this is often described by saying that Einstein didn't succeed in unifying gravity with matter, but a better statement would be to say that on a logical plane, he unified gravitational forces with matter, but wasn't satisfied with the form of matter that the resulting theory predicted. So on a conceptual plane, it's a great triumph that merely trying to describe gravitational forces, finding the logical framework, which is Riemannian geometry, writing down the simplest equations in that framework, which are nonlinear equations, one then found that one had not merely a theory of gravitational forces, but a unified theory that unified gravitational forces with matter. However, this wonderful unified theory has a couple of flaws. It's incompatible with quantum field theory. That, of course, wasn't known at the time, since quantum field theory was invented later. But evident even at the time was that the forms of matter predicted in this theory were less rich than those that we observe. Now, I would next like to give a heuristic account of why what string theory is and why it might be hoped to improve upon general relativity. The framework for this really does require some preliminaries about quantum field theory, and I do hope to give a brief comment about quantum field theory later. But without developing all the requisite preliminaries of quantum field theory, I would like to at least explain heuristically how one stumbles upon some generalization of general relativity in the form of string theory. And in doing so, I will be explaining conventional things in quantum field theory in a way which is closely related essentially to the viewpoint introduced by Polyakov some years ago. Well, in quantum field theory, the scattering of particles, such as the gravitons of general relativity, are described by Feynman diagrams. Now, a Feynman diagram is a space-time history of a scattering process. In this transparency, I've sketched a space-time history. Time runs vertically on the diagram. Space, or one of the space dimensions at least, runs horizontally. Particles have been emitted and absorbed at these points A, B, C, and D. The solid lines are actually curves in space-time along which a particle traveled. And X, Y, Z, and W denote points in space-time at which one particle split into two, or in which two particles recombined into one. So this actually is a sketch of a sequence of events in space-time. And if you start with some theory like general relativity, then the rules of quantum field theory will give you algorithms for associating probabilities with space-time history such as that one. Actually, you start with some abstract graph gamma, and then you imagine some map of gamma into space-time, which I'll call capital X. X denotes a map of gamma into space-time. Of course, this graph gamma is a collection of intervals. If we map such an interval into space-time, we can compute its arc length. And the sums of those arc lengths is what I'll call I of X, the length of the image of this graph gamma in space-time under some map in which gamma is mapped into X of gamma. So let omega of gamma be the space of all maps of the graph gamma into space-time. Now, in conventional quantum field theory of the last 50 years, even though this isn't quite the conventional way of describing the usual structures, one almost standard way to describe the usual Feynman diagrams is as integrals over this path space, omega of gamma. So we have an abstract graph gamma, we map it into space-time. Here I've sketched the image of that graph on such a map. Omega of gamma is the base of all such maps. I is the length of the image of the graph under that map. We try to integrate over omega of gamma, e to the minus the length of the image of the map, times some factors I'll explain presently. The local factors at the branch points in the graph. Now, one thing you'll note here is that infinite dimensional integral, the integral over the space omega of gamma, of all conceivable maps of this graph into space-time, all conceivable continuous maps of gamma into space-time. That's a characteristic infinite dimensional integral that appears in Feynman path integral formulations of quantum mechanics and quantum field theory. Now, one thing which we'll notice here is that when we're mapping this graph gamma into space-time, gamma is not a manifold. It's almost a one-dimensional manifold, but actually it's a one-dimensional manifold with singularities P, Q, R, and S. And the ills of quantum field theory all come about because gamma isn't a one-dimensional, isn't a manifold, but has singularities. We're taking this graph, which is a one-manifold with singularities, we're mapping it into space-time, and two bad things happen because of the fact that gamma isn't a manifold. First of all, well, we have to define this infinite dimensional integral. And in fact, there's a lot of experience and even some theorems in constructive field theory about defining such infinite dimensional integrals. And one thing we know about it is that it will work a lot more nicely if you tried mapping a smooth one-manifold into space-time rather than a graph with singularities. When we map such a graph into space-time, we encounter the possibility that the image of P, Q, R, and S in space-time may coincide. And in fact, after we've learned to define such infinite dimensional integrals in the first place, we learn that this integration is badly behaved near the region where x of p, x of q, up to x of s all coincide. This bad behavior makes all quantum field theories difficult to define, but actually impossible in the case of general relativity. So our first problem in quantum field theory, its overall mathematical difficulty, and in particular its incompatibility with gravity, arises because gamma isn't a manifold. Secondly, because gamma isn't a manifold, we have these special points, p, q, r, and s. And we had a nice simple factor in the integrand, the exponential of minus the length of the image of gamma in space-time. But since there are these special points, p, q, r, and s, it makes sense, as those points are singled out, to take some local functional of the behavior of x near one of those points. Phi here is a local functional of x of p and the derivatives of x near p. It makes sense to pick such a local functional and introduce a factor in the integrands at each of those singular points, p, q, r, and s. And in fact, with certain very simple limitations, each choice of this local functional, phi of p, gives you a different quantum field theory. The infinity of quantum field theories corresponds to the infinity of local factors that can be introduced at those branch points. Well, of course, you might think that we're straining things a bit and that there'd be a minimal model where we don't introduce these factors. But one of the surprises, perhaps, is that that isn't true. If you take a nice geometrical theory, like general relativity and Yang-Mills theory, and transform it into this framework, you'll definitely need some suitable local factors at those points. And on the contrary, the theories that wouldn't have those local factors, or would have simple local factors, turn out to be quantum field theories that don't have interesting geometrical content. So this is a freedom, not only it exists in principle, but we have to use it, and we do use it, for the quantum field theories that are of most interest in physics. So we have a variety of problems which have their origin in the fact that gamma isn't a manifold. Suppose, though, that we wish to ask an engineering shop, let's say, to make a physical model of the graph gamma. Well, we probably defined this graph as consisting of mathematical lines, but the craftsman doesn't have mathematical lines at his disposal, so perhaps if we're lucky, he uses thin tubes. And if he uses hollow tubes and joins them smoothly as a plumber does, then we can replace this graph by something for which it's more easy to make a physical model, which looks very similar from a big distance. And that is actually why string theory, if viewed coarsely, looks rather like quantum field theory. But there's a fundamental difference. In replacing these mathematical lines with little tubes, we've replaced the one manifold with singularity, gamma, by the smooth Riemann surface, sigma. Now, in some sense, the graph gamma may be an approximation to sigma. But the fundamental difference is that sigma is a smooth manifold, which gamma isn't. And as a result, in replacing gamma with sigma, we in fact overcome both the infinities in quantum field theory and also the lack of uniqueness. The lack of uniqueness came from the ability to attribute special factors with these points. Upon losing those special points, we in fact encounter a situation in string theory where we replace gamma with sigma, in which there are very few theories that can be formulated. Now, the other main occurrence which arises when we replace gamma with sigma, let's take a close-up of this picture, which I won't draw completely. Remember, this is actually a picture of a process occurring in space-time. So time is running upwards in the picture. And this graph gamma, which I've drawn, is actually happening in space-time. It actually describes the propagation in space-time of point particles, which for general relativity are the quantum counterparts of the waves that I sketched earlier. So I'm going to take a blow-up of a little piece of that picture. Our blow-up is the propagation of a particle in time, in space-time. If we take its locus at given time, we get a single point, or at most a finite set of points. The fact that we might get a finite set of points instead of a single point leads to the fascinating story of creation of matter and antimatter, but perhaps it would take us too far afield to discuss it. So I'll imagine that we find the locus at a given time to be a single point, and that corresponds to saying that this graph is a theory of a point particle propagating in space-time. If, in the same way, we take the locus at fixed time of one of these tubes, it consists of a circle, or perhaps a finite collection thereof. So we've actually replaced the point particle of field theory with the oscillating circle. You see, I remarked that on a conceptual plane, Einstein had unified gravitational forces with some kind of matter, but the matter in question wasn't rich enough. And it wasn't rich enough essentially because that point particle, which was the locus of a curve at given time, didn't have enough freedom. When we replace our graph with a Riemann surface sigma, the locus at given time isn't a point or a finite collection of points, but consists of circles, and one of those circles, or in that case closed strings, will be rather like a violin string, except without fixed endpoints. Physically, it will oscillate in time, and like a violin string, it will have an infinite set of harmonics, which will correspond to different forms of matter. So in fact, replacing gamma with the Riemann surface sigma means that one is dealing with a theory with much richer forms of matter. It's not at all obvious from what I've said that these richer forms of matter will be at all like what we find in the real world, but upon closer investigation it turns out that they are. So the seemingly innocent step of replacing gamma by sigma leads us to a more unique theory with also a much richer form of matter. And it leads us at the same time into the world of Riemann surfaces and modular forms and representation theory of certain infinite dimensional Lie algebras, such as diff S1, the group of diffeomorphisms of S1, which will act on this circle. Now, I have another transparency which aims at recapitulating what I've been saying. So in a theory like general relativity, we have really basic formulas, like the geometrical action principle, the integral over space-time of the Ricci scalar. The beauty or lack of beauty of such a theory should be judged by the beauty of its fundamental principles. Our aspiration would be to generalize this elegant geometrical action principle to some richer structure that will be compatible with quantum field theory. Direct and even indirect attempts to do so haven't been successful. On the other hand, if we consider not the really fundamental formulas of Riemannian geometry, but some derived formulas, such as the ones I've been discussing involving maps of graphs gamma into space-time, then it turns out that some of the derived formulas can be generalized. Now, of course, if at the top of everyone's mind was that we think of general relativity in terms of maps of graphs into space-time, then this generalization would be more obvious and perhaps would have happened sooner. What makes it less obvious is that although this is closely related to standard descriptions of what one gets from quantum field theory, it's not the most standard description by any means. I haven't explained the steps in quantum field theory which lead from fundamental formulas to less fundamental formulas involving these graphs. It's possible to explain it, but it would have taken an excessively long exposition. If we work on this less refined plane, we find we can generalize the less fundamental formulas of quantum field theory, getting something called string theory, which overcomes many of the difficulties. For instance, the lack of uniqueness of quantum field theory which in this framework arose from the fact that the Ricci scalar is only one of many possible geometrical action principles. In this less refined framework, it is associated with the fact that gamma isn't a graph. Gamma is a graph, but not a manifold. And that is eliminated in going to Riemann surfaces. And so on with other points I've already illustrated. So what has happened in the invention of string theory is that in a peculiar process of trial and error with many historical stages, one has succeeded in generalizing not the truly fundamental formulas of older physical theories, but some of the derived formulas. Now, just as this picture with the graph gamma is to be derived from some much more fundamental viewpoints, the same ought to be true with our generalization of it involving Riemann surfaces. And elucidating what lies above the Riemann surface in the sense that general relativity lies above these graphs is what I've alluded to as the mystery of unraveling the logical structure behind string theory. And I personally believe that it's a very fundamental problem for both mathematics and physics. One peculiarity is that ordinarily the beauty of a theory is to be judged by its fundamental principles and not to be looked for in these derived formulas. Derived formulas like the ones involving graphs and maps of graphs into space-time are necessary tools if you want to determine the quantitative predictions of a beautiful theory like general relativity, but they're not the basic formulas and they're not necessarily beautiful. In fact, they're ordinarily not beautiful. One of the surprises in string theory is that the Riemann surface generalization of the theory of those graphs is very beautiful. It involves fascinating properties of Riemann surfaces, modular forms, infinite dimensional representation theory, algebraic geometry. Some of the many beautiful aspects of this were described in a marvelous article by Manin, which was submitted to this conference, but which regrettably he wasn't able to deliver here because of not being allowed to attend the conference. But Singer presented them very elegantly in a talk on Tuesday afternoon. One shouldn't expect beauty in trying to generalize a secondary formula, but actually in the case of string theory, one finds that the generalization of this picture with the graphs leads to very fascinating and beautiful mathematics. And I personally would conjecture that what lies above here will in some sense stand in the same relation to general relativity, that the marvelous automorphic forms and algebraic geometry that enters in Riemann surfaces, path integrals from Riemann surfaces, compares to the older Feynman diagrams of field theory. Now, I haven't been able to explain how one goes from here to here. That would be rather too time-consuming. I do want to use the remaining time to explain briefly a little bit of the flavor of what it means when we talk about the maps over infinite dimensional spaces that are involved in dealing with these graphs gamma or the Riemann surface sigma in their own terms. So in the rest of this talk, we're going to be working on this lower half of the page without discussing how this one is associated with conventional field theory. Now, in doing this, I will be giving a very brief introduction to quantum field theory, since I will have to attempt to extract one or two ideas in about 15 minutes. You see, quantum field theory exists on the upper half of this page because we started with quantum gravity, or an attempt at quantum gravity, in going here, but quantum field theory lives again at the lower half of this page because these infinite dimensional integrals are really formulas in quantum field theory. Now, quantum field theory has been, for most of its 60 years, almost the private preserve of physicists. And even now, it has not yet emerged as a mathematical tool. But there are reasons to believe that quantum field theory might emerge as a mathematical tool in the near future. Reasons independent of string theory for believing that, because there are at least two areas where progress in mathematics has come to the brink of quantum field theory. That is, areas of mathematics where some characteristic features of quantum field theory have begun to be recognized as significant. One of these is the representation theory of affine Lie algebras, which Frankel reviewed yesterday, and which is closely related to the Hamiltonian picture of certain quantum field theories. And the other involves recent work in arithmetic geometry, which we will hear about in the next lecture, where the Dirac determinant, which is one of the really fundamental characteristic ingredients in quantum field theory, has begun to play an important role. So, in a choice of topics for an extremely brief comment on quantum field theory, I'm going to talk about points that are relevant in string theory, but also might prove to be related in further developments to the areas of mathematics I've just mentioned. Let then sigma be a Riemann surface, perhaps with boundary. Let phi, taking sigma into the real numbers r, be a real valued function. And then let's define an action, very natural action, which is called the action functional of free boson field theory, the integral over sigma of this 2 form, del phi wedge del bar phi, where del and del bar are the the natural operators associated with a complex structure on sigma. Let f be a real valued function on the boundary of sigma, and let omega sub f of sigma be the space of real valued functions on sigma whose restriction to the boundary coincides with f. Now, we didn't need a Riemannian metric on sigma in defining the action I, but if sigma is endowed with a Riemannian metric and not just with a conformal structure, then this affine space omega f of sigma likewise has a natural metric, which I've defined here by giving the distance between 2 functions phi and phi prime. Now, in finite dimensions, a Riemannian metric certainly induces a measure, the so-called square root of the determinant, if you wish to write it in formulas. And hoping that that works in infinite dimensions, we might try to define what I'll call z sub f of sigma, which is the integral of e to the minus the action over the space of functions whose restriction to the boundary coincides with f. That's what I called omega f of sigma. The integration measure is the one which we hope was induced by that Riemannian metric on sigma. Well, how are we going to integrate in infinite dimensions? Well, physicists actually deal with infinite dimensional integrals that are very difficult to define mathematically and for which you can't write explicit formulas. But I happen, for practice, to have given you one for which we can write an explicit formula. I, in this case, was a quadratic functional of phi. So we're integrating the exponential of minus a quadratic functional. That's a Gaussian integral. And we know that Gaussian integrals are integrals which are easy to evaluate in finite dimensions. Let A be a quadratic form in finite dimensions. If we're integrating in finite dimensions the exponential of minus a quadratic form, we can carry out that explicitly in terms of the square root of the determinant of A. Or if we have a natural basis in phi, so it makes sense to speak of eigenvalues of A, we can write the answer in terms of eigenvalues of A. So we can try to interpret Gaussian integrals in infinite dimensions in a similar way. First, consider the case where the boundary of sigma is 0. The same action I wrote earlier can be written like so, in a way that makes the conformal invariance less obvious, but some of the differential geometry more obvious, perhaps. What the operator that appears here is the ordinary Laplacian. And delta plays the role of our quadratic form in finite dimensions, so we should study the eigenvalue problem, delta phi equals lambda phi. It's a nice eigenvalue problem, a nice discrete set of eigenvalues. And formally, we would like to define our integral as the product of the minus half powers of the eigenvalues. Well, of course, this has a 0 eigenvalue, which we should throw away. And it also is a little bit divergent because of the infinite factor. But nonetheless, there are many natural ways of regularizing this. One elegant way of doing it is so-called zeta function regularization. We introduce the zeta function as sum over eigenvalues lambda to the minus s, and then we write a formula which would be correct in finite dimensions if this were a finite sum. With an infinite set of eigenvalues, the zeta function converges for a large enough real part of s, and we take here its analytic continuation to s equals 0. This would be our zeta function definition, and there are many other definitions, such as the Pauli-Villars method used in quantum field theory some 40 years ago. If now the boundary of sigma is not empty, and we're given a real-valued function on the boundary, we'd like more generally to define the integral not over all maps of a sigma into space-time, but only maps of sigma into R, but only maps which coincide with f on the boundary. Well, for f equals 0, what we've already said is quite adequate. For f equals 0, we're still integrating a Gaussian integral on a linear space. We study the eigenvalue problem with boundary conditions that the eigenvalue vanishes on the boundary, and we make again the same definition. If f isn't 0, then by classical theorems we find there's a unique minimum of this functional subject to the condition that the boundary value is equal to phi. Let phi naught be the extremizing function, and let our integration variable phi be phi naught plus some correction. Then we can easily work out by manipulations that would be valid in finite dimensions the appropriate formulas. It turns out in this case that the action, because it's quadratic, for phi is the sum of the separate pieces. And if phi has boundary value f, then phi prime has boundary value 0. So shifting the integration variable from phi to phi prime, we would work out a formula. Now, in reaching this point, we've needed a metric on sigma. We needed to claim that these spaces, omega of sigma, had measures, and we induced the measures from Riemannian structures on sigma. So since we need metrics on sigma to reach this point, these formulas are actually not conformally invariant. If we make a conformal rescaling of the metric of sigma, which of course won't change its conformal structure as a Riemann surface, then this formula won't be invariant. However, it's possible to work out simple formulas for how it transforms under conformal transformations. To physicists, those simple formulas involve the so-called theory of anomalies. And to mathematicians, they involve the theory of the determinate line bundle, as it is entered in the work of Faltings, Deligne, and Atiyah and Singer, and more recently Fried and Bismuth and others. I've given a case, well, more generally, if one considers simple generalizations of this, one will be led to generalizations of these formulas whose behavior under conformal rescalings of the metric involve a quite rich theory, which involves the theory of certain holomorphic line bundles over the moduli space of Riemann surfaces in its mathematical exposition. But it wouldn't be practical to enter into that here. I'll content myself simply with saying that I've tried to give a prototype of some of the manipulations by which we're led to investigating determinants of operators such as the Laplacian, and for surfaces without boundary, such that we wouldn't have that factor here. This is a simpler prototype of some of the things that enter in the next lecture. Now, I'd like to conclude by returning to our more general themes. I suppose it would be plausible to conjecture that in some suitable sense, the number of really fundamental problems in mathematics is infinite. But I personally believe that the number of really fundamental physics problems is finite. And therefore, by definition, a physicist who has the privilege of working on such problems is lucky, since in the course of time, progress will slow, either by solving them or by failing to make further progress. If it's true that the number of really fundamental physics problems is finite, then the number of episodes in the future in which there will be really fundamental interaction of mathematics and physics will likewise be finite. However, there are reasons for believing that the next few decades will be one of those epochs.
So let us begin informal seminar on which Professor Witten will speak on gauge theories and Jones polynomials. Professor Witten's work was already introduced to you in the first day, so he needs no more introduction. So I give floor to Professor Witten, please.
Thank you. I'm very glad this is an informal talk, as a result of which my wife hasn't required me to wear a suit. So I will be describing a particular three-dimensional quantum gauge theory which puts the Jones polynomial and it's in a manifestly three-dimensional form, exhibiting its symmetries, which are not obvious from the original definitions. And also, although I won't have a chance to talk about this, exhibits its formal analogies to modular moonshine, that is, moonshine in the theory of the monster group and the theory of affine Lie algebras, modular invariance in those theories, a Donaldson theory, and other things. And also gives a context in which the quantum group quantization of an ordinary Lie group arises from ordinary geometry. For special gauge groups, this theory is also related to some other things, including three-dimensional quantum gravity, the Casson invariant, and some of the fashionable models of high-temperature superconductivity. So I thought that, I'd begin the talk with a little bit of the end, just as an inducement. So remember that on the first day in explaining von Jones's work, Joan Berman explained a bit about scheme theory and also indicated the history of the scheme theory idea that I'm about to summarize and the people who contributed to it. So this is a very pretty picture where you have three pieces of knots. These pictures are meant as pieces of very complicated knots, which I won't draw. But you have some complicated knot, and inside the dotted line it just looks like this, or this. And you consider three knots which are the same outside the dotted lines of some projection, but inside a little sphere which has been projected onto the plane. You have these three different pictures, and you have three complex numbers, alpha, beta, and gamma, and you define an invariant of a knot by saying that the invariants of three pictures that are the same outside and look like this inside, weighted by complex numbers alpha, beta, and gamma, add up to 0. By an elementary induction, it can be seen that this property uniquely defines a knot invariant if it exists, but the fact that it does exist is considerably deeper, and in a way is this part of the surprise of the Jones polynomial and its generalizations, the Humphrey and Protitsky, Tracek and Kaufman polynomials and others. Now, the explanation we will get for this beautiful picture is as follows. You see, the boundary of this sphere has 4 marked points where the knots pass through the sphere. And we will find a natural way to associate a two-dimensional vector space, which I call H sub S, to every sphere S with 4 marked points. It's a two-dimensional vector space, and that's why there are 3 terms in this skein relation. The association of the vector space to every sphere has the property that every Bordism determines a vector in this space. Now, by a Bordism, I mean a 3-manifold which has for boundary the sphere, and in which the marked points are boundaries of bits of knots. These lines are only permitted to end at those 4 points. So, this picture here, we have the same boundary in the 3 cases, but the interiors are 3 different Bordisms. And in this theory, every Bordism determines a vector in H sub S. And we will have in this theory a knot invariant in which the details of the interior of S don't matter. All that matters from the mess that might be inside S is this vector psi sub b in the Hilbert space on the boundary. Now, a simple fact of linear algebra is that any 3 vectors in a 2-dimensional space obey a linear relation. Alpha psi 1 plus beta psi 2 plus gamma psi 3 is 0. For some complex numbers, alpha, beta, and gamma. In this case, we take the 3 vectors determined by these 3 Bordisms, and they obey some linear relation. And if you glue them into some more complicated picture, so that these are little pieces of knots which are constant outside the sphere and look like this inside, then this relation is a relation between the values of the invariant for 3 different knots. So the existence of this theory, now the characteristic of the theory will be the values of alpha, beta, and gamma, and such a theory predicts the validity of scheme theory, that is, the ability to define a knot invariant this way, for a particular value of alpha, beta, and gamma. To explain scheme theory in general, we need a 2-parameter family of such constructions so that the ratios of alpha, beta, and gamma are variable. So that's the answer we will eventually get, although perhaps not completely explained today, for the validity of scheme theory. It comes fundamentally from the existence of a knot invariant which can be computed where the details of what's inside any little sphere don't matter. All that matters is the vector that Bordism determines in the 2-dimensional vector space. Now, put this way, it's an elementary topological idea, but its geometrical realization will bring us into matters that may seem rather far afield at first sight in the realm of quantum field theory. Well, we will be doing quantum gauge theory, so we pick a gauge group G. G is a Lie group which, for economy of exposition, we take to be connected and simply connected. This simplifies the discussion. It's not essential, but it simplifies the discussion because then every G bundle on a 3-manifold is trivial. We don't necessarily assume that G is compact, although we will sometimes assume it. Again, for simplicity only, we assume that G is simple. In that case, up to a scalar multiple, there is a unique invariant quadratic form on the Lie algebra of G. And we denote it as the trace. We denote the pairing of 2 elements as the trace of their product. The motivation being that it can actually be realized as the trace in some representation. And the normalization I'll give in a second is such that for SUN, this scalar product is the trace in the n-dimensional representation. Now, a G bundle E on a 4-manifold X has a characteristic number which can be computed by taking the curvature of any connection and integrating trace of F wedge F. And our normalization of the trace is such that this is integer valued. So that's a topological invariant on a 4-manifold. The corresponding secondary Chern-Simons invariant isn't a topological invariant, but is an invariant that depends on a connection. If we have a 3-manifold M and a G bundle over it and a connection on that bundle, then there is a corresponding secondary invariant. So the bundle is called E. We extend the bundle and the connection over some 4-manifold B, and we define the The three-dimensional secondary invariance is the integral over the bounding form manifold of the object which on a closed form manifold would have 2 pi times integer periods. The fact that for closed manifolds the periods are 2 pi times integers means that for a manifold of fixed boundary, this depends on the extension only up to a multiple of 2 pi, integral multiple of 2 pi. So this is well defined with values in real numbers modulo 2 pi times integers, or in other words, its exponential times the square root of minus 1 is well defined with values in u1. Now, we're going to be studying a certain quantum gauge theory in which the Lagrangian is a positive integer k times this functional I of a. And this integer k is related, as it turns out, to the level in the theory of affine Lie algebras. Now, as is standard in quantum field theory, the discussion has two halves. One is the construction of Hilbert spaces, and in this case, they will be generalizations of the Jones representations of the braid group. And the second part are path integrals. Although it's hard to explain this just in one lecture, the questions we will ask and the methods we use are not dreamed up on an ad hoc basis for this particular problem. They are the techniques of quantum field theory adapted to this situation, albeit a somewhat unusual situation in which some steps that are usually relatively trivial become non-trivial. Now, the goal of the first step of the discussion is to associate a Hilbert space H to every 2 manifold sigma, every closed Riemann surface sigma. And this is accomplished in general in quantum field theory. So we're in 3 dimensions, but in the Hamiltonian version we are in 1 dimension less, here 2 dimensions. We consider manifolds without boundary, and for every such we wish to find a Hilbert space. And this Hilbert space is constructed by quantizing a suitable symplectic manifold, which in general is the moduli space of critical points of the Lagrangian on a particular 3 manifold, which is the surface times R1, that being time. Now, Fleur discussed the same functional in another context, and as he explained, a critical point of this functional is a flat connection, or in other words, a representation of the fundamental group of M into G. Now, since pi1 of M is the same as pi1 of sigma, the moduli space of such representations is the same as the moduli space of flat connections on sigma, and this is the space we will quantize. Now, this space is often studied by people studying Riemann surfaces, but here, in principle, it's arising as a representation space of a certain 3 manifold. It happens that that degenerates to representations of the fundamental group of sigma because M is contractible to sigma. But in principle, this space is originating with a 3-dimensional origin, which is the beginnings, in a very elementary level, of the 3-dimensional explanation of the Jones polynomial. Now, as a preliminary, which is usually trivial in quantum field theory, but here non-trivial, we have to consider what kind of object is the Lagrangian on a 3 manifold with boundary. And here I will be explaining what Constant and Suryo call pre-quantization in this context, but I'll be explaining it in some detail when we actually get to quantization. I won't go into such detail. So remember how we defined the action functional. We had a 3 manifold without boundary. Then we regarded it as the boundary of some 4 manifold B, and the action was defined as an integral over B. So implicit in this is that the boundary of M was 0, so that M was the boundary of some B. Now we want to let the boundary of M be non-zero, and this definition therefore doesn't make sense, and therefore we don't have any. We in fact no longer have this Chern-Simons functional as an R mod 2 pi z valued functional. However, what is the nature of the abstraction? That curly A will be the space of connections on this surface sigma. Then we can't define this exponential of the Chern-Simons function as a number, but we will define it as a section of a line bundle over the space of connections. Or more precisely, a connection on the 3 manifold has boundary values in A, and for every point in A, we have a one-dimensional complex vector space, the fiber of a line bundle at that point. And this thing will not be a number, but will take values in the fiber of that line bundle. So the line bundle is really defined just by asking what's the obstruction to defining this as a number. Well, the obstruction was that we had an open 3 manifold, and if we knew how to close it, we could get a number again. So we just exploit that systematically. We have this space of connections. To describe a line bundle over the space of connections, we must, for every point in that line, in that space, describe a one-dimensional complex vector space, V sub A. And we declare that V sub A has a basis which we call A prime for every extension of A over any 3 manifold Z. Z is any 3 manifold, and A prime is any extension of the connection over Z. Actually, we also extended the bundle and connection over Z. And for every such extension, this line has a basis A prime. Well, I need to tell you how to compare 2 different basis elements, and I can do this because if A prime and A double prime are 2 such extensions, individually they don't have a Chern-Simons invariant, but they have a relative Chern-Simons invariant because they have the same boundary by definition. So if I glue them together with opposite orientation, we get a closed 3 manifold. And then the connection on the closed 3 manifold has a complex number valued invariant. And we just say that A prime is A double prime times this number. So now, although we have no natural basis in this one-dimensional vector space, we've defined a one-dimensional vector space for every connection on the surface. And thus, as the connection on the surface varies in the space of all such connections, we get a line bundle L over the space of connections on sigma. Now, this line bundle has a natural unitary connection. In fact, if we're given a path in the space of connections, so A1 and A2 are connections on sigma, on the surface sigma, and gamma is a path between them in the space of connections, that path gives us a connection on a certain 3 manifold. The 3 manifold is sigma times the unit interval. And on sigma times the unit interval, we take the connection which is trivial in this direction, and which in this direction is A1 at this end and A2 at this end, and interpolates between them by the given path. So that's a connection on a particular 3 manifold. And now if you tell me how to extend A1 over some 3 manifold, then I know how to extend A2 over some 3 manifold, because the interpolation from A1 to A2, which we just discussed, can be glued onto your interpolation. And that gives a unitary connection on this line bundle. In other words, if you give me a trivialization of the fiber at A1, I've given you a trivialization of the fiber at A2, which depends on this path. And we interpret that as parallel transport of the trivialization here to a trivialization here along that path. Now, let G hat be the gauge group of maps of this surface into G. Then G hat acts on the space of connection along sigma, and with a small effort that actually requires a slight elaboration of what I've said, the G hat action lifts to an action on this line bundle, preserving the connection. Now, we have a projection from the space of connections to connections modulo gauge transformations. We can ask whether the line bundle with connection descend, and they don't. The standard criteria aren't obeyed. If you take a little loop downstairs and lift it to a loop upstairs, the holonomial on the loop will depend on the lift, and therefore there's no way to make these things descend. But if we restrict ourselves to flat connections, the space of flat connections on sigma, then by elementary considerations, you see that this line bundle and connection do descend to a line bundle and connection over the space of flat connections divided by gauge transformations. And that was the moduli space of flat connections on this surface, which I indicated earlier was going to enter. So we get a line bundle with connection over the space of flat connections on sigma. Its curvature can be computed in an elementary fashion and is the standard symplectic structure, which was first related to gauge theories by Atiyah and Bott in a paper that Karen Uhlenbeck mentioned, is the standard symplectic structure on this manifold. Now, these things have been studied in the past in other methods, and in particular, this line bundle and connection in special cases are usually constructed by picking a complex structure on sigma and using algebraic geometry. If you pick a complex structure on sigma, so that sigma is a complex Riemann surface, then by the Noah-Simcha and Seshadri theorem, this moduli space is a moduli space of holomorphic bundles on sigma, and then one has the determinate line bundle with its Reisinger-Quillen metric, and its curvature as computed by Quillen is precisely the same curvature as this thing. So there's a holomorphic construction in special cases like the unitary group, or for any group for special values of k, there's a holomorphic construction of this line bundle that depends on picking a complex structure on sigma. What we've achieved by the construction I've given is that we've given a purely topological construction. It doesn't depend on any complex structure. The mapping class group acts in a fashion which is visible, essentially. And at the same time, we've related the construction to three manifolds. What we've achieved is actually what Costant and Suriel call pre-quantization in this problem. We've constructed what is called the pre-quantum line bundle, and we've constructed it in a way that doesn't break this topological invariance of the problem. And you see, the construction was naturally related to thinking of it in relation to three manifolds, which is what we want because we want to do a three-dimensional problem. Now, going back to the original question I raised of what is the Chern-Simons invariant I of A, if A is a connection on a three-manifold with boundary, well, we see that tautologically it makes sense as a section of this line bundle that we introduced, or more exactly, a vector in the appropriate fiber of that line bundle, because any trivialization of the line bundle, which is an extension, a bounding three-manifold and an extension of the connection, enables us to make sense of that thing as a number. So this is pre-quantization in this situation. Now, not only have we pre-quantized, that is, we've constructed the appropriate line bundle over the right moduli space, which has the right unitary connection and the right curvature, and without breaking any of the symmetries of the problem. But we're in a very good situation because this moduli space is the symplectic quotient of an affine space. The affine space is the space of connections, and you see, we took two steps. We restricted to flat connections and we divided by the gauge group. And although I won't explain it, those combined steps, mathematicians call them the symplectic quotient, and for physicists they go back to Newton's use of symmetries to reduce a problem in mechanics. But anyway, this rather complicated moduli space of flat connections, we're seeing it in relation to an affine space A with a group action. And this relation, of course, between the two is what was exploited by Atiyah and Bott to compute the cohomology of this moduli space. But here we're seeing the same, we will be using the same relation in a different way that's appropriate to this particular quantum field theory. Now we want to quantize, and I won't have time to explain quantization in as much detail as I gave for pre-quantization, but quantization means associating a Hilbert space H, which should be canonically associated with the data, and the data are a moduli space and a line bundle with connection. But these data were canonically determined by this surface sigma, as we saw. So we will really be canonically associating a Hilbert space with the surface sigma. Now, What quantization means in general is a long story, but if there were a natural complex structure J on this moduli space M, obeying certain conditions, most importantly, that the symplectic structure, the curvature of this connection should be of type 1,1, so that the line bundle would get a natural holomorphic structure. And in addition, the symplectic structure should be positive relative to that complex structure. If there were a natural complex structure, then the quantum Hilbert space would be, you see, if we had such a complex structure, then our moduli space we take as a complex manifold, and the conditions mean that the line bundle is a holomorphic line bundle, and at level k, we would take the kth power of that line bundle and take its holomorphic sections. And that would be our Hilbert space for the level k theory with this gauge group and associated with this surface sigma. Well, there isn't a natural complex structure on M, but for every choice of complex structure on this underlying surface sigma, we have a Hodge decomposition of cohomology. You see, the tangent space for this moduli space is the Durand cohomology of sigma with values in a twisted bundle, and if we complexify it, then it has a Hodge decomposition, and that Hodge decomposition is really then a complex structure on this moduli space. In fact, it's precisely the complex structure predicted by the Narasimha and Seshadri theorem, and I will call it by the same name J. So for every complex structure J on the surface, we get a complex structure J on this moduli space, and thus, by the definition on the last transparency, for every complex structure J, we can make this definition, but if J is not natural, then neither is curly H. So we have a definition of curly H, but it depended on J, so I'll call it curly H sub J. And because of the J dependence, well, this situation to begin with is fibered over the space of all complex structures on sigma, but it trivially reduces to the space of complex structures up to isotopy, or in other words, to Teichmüller space. So we really have a situation that's fibered over Teichmüller space. We have this family of Hilbert spaces fibered over Teichmüller space. Actually, without mentioning it, I started to assume a transparency or two ago that this, well, I didn't prove that the Hodge decomposition gave a complex structure. That really, at that point, was assuming the case of a compact group. For other classes of Lie groups, we'd get something, but not quite this. So we're now assuming for the moment that we're dealing with a compact group. Now, we wanted a single Hilbert space, and we have a family of them. And of course, to get back to the situation of a single Hilbert space, what we want is a natural flat connection on this bundle. Such a flat connection, since the base Teichmüller space is contractible, such a flat connection would give us a natural identification of the fibers. Such a connection can be explicitly and rigorously constructed, as I did along these lines with Axelrod and Della Pietra, using two facts. The first fact is that if we were quantizing an affine space, such a flat connection exists because of the Stone-von Neumann theorem on the unique representation of the Heisenberg group, and physicists think of this flat connection as the infinitesimal generator of what we call Bogoliubov transformations. And then one can push down from an affine space to its symplectic quotient by restricting to the G invariant subspace. Now, for finite dimensional affine spaces, these two facts would give the result a priori. Here, the affine space is infinite dimensional, only the symplectic quotient is finite dimensional. So what one has to do is to take the formulas which would be valid a priori in the finite dimensional case and do a little bit of geometry to verify them and in fact modify them slightly so that they make sense in this case for only downstairs you have a finite dimensional story. Now, the flat connection one gets this way, or I've written it in the plural because there were different groups and levels. These flat connections, since the mapping class group acts here, one really gets representations of the mapping class group, and as was first perceived by Tsuchiya and Kanya in a work that was part of what made possible this whole development, these are generalizations of the Jones representations of the braid group. To get precisely the Jones representations, you would take sigma, the surface, to have genus 0, and you would have to include knots and marked points in a way that I haven't indicated. Moreover, the equations that define this flat connection are the generalizations to genus J of the Canisian Exam-Lodchikov equation, which we've heard so much about in so many different talks at this Congress, starting with Jimbo's talk explaining part of the work of Drinfeld, and including unexpected applications to number theory that were mentioned in one of the plenary addresses yesterday. Now, this construction of this particular flat connection for compact G has been obtained in other ways. While the original results came from conformal field theory about 6 years ago by Knizhnik and Zamolchikov in genus 0, and Noguchi and Uguri some years later in genus 1. And these authors were studying the, well, what's sometimes called the Wessamino-Novikov-Witten model of conformal field theory. And then these constructions were formulated rigorously and in arbitrary genus by Tsuchiya et al. Tsuchiya talked about it yesterday. And there's a simple argument, well, there's a simple sketch of an argument by Siegel in the Swansea proceedings from 2 years ago. Also, it's possible to construct this connection by pure algebraic geometry, and this has been done by Hitchin and by Bailenson and Karjan. The construction I've indicated is natural in relation to 3 dimensions, in the sense that it's the one that arises naturally as the solution to quantization of this pre-quantized symplectic manifold. And it extends to other classes of gauge group, which we hope may also be the case for some of the other approaches ultimately. In fact, with some relatively minor modifications of what I've said, it's possible to carry out a similar construction if G is a complex semi-simple Lie group. Now, perhaps I'll devote one transparency to a slight digression. So far, there are no results about this problem for other classes of Lie group which one would like to study, and notably for non-compact real forms, even in the simple case of SL2R. Now, in a very precise sense, which would take us far afield to really explain, this subject is a generalization of representation theory, and from that point of view, the facts I've stated aren't too surprising. So in representation, you know well that compact groups are the easiest, followed by complex groups, and that the non-compact real forms are an order of magnitude harder and difficult to study in a unified fashion. So I've told you that again in this context. I had a transparency alluding to different approaches for the compact groups, and the corresponding problem for the complex groups is definitely harder and is much less well understood, but it is tractable. It's the next case after the compact groups. It leads, of course, to infinite dimensional Hilbert spaces, just as in representation theory, where the unitary representations are infinite dimensional. And the solution of this problem for complex groups is related to compact groups, much as in the case of representation theory. Since there are no results for the non-compact real forms, one doesn't know what will happen, but either there's some reasonable way to solve this problem which might well lead to some new viewpoint in representation theory, or this problem might be afflicted with more elaborate versions of the usual difficulties in representation theory. Well, we now come to the deeper part of the story, and while I wish to emphasize that what I've said up until this point is very precise mathematically, in proceeding, we will have to base ourselves for a while on the massive experience in theoretical physics in the last 40 years. Though at the very end, we will get back to the realm of precise, rigorous mathematics as of our period. So, I might say as a general rule, I'm explaining a particular quantum field theory, and in this particular quantum field theory, The deeper results are based on the ideas that I will indicate. But there's a similar statement that can be made about other quantum field theories of geometrical interest. For instance, if one is interested in what was called by Conway and collaborators monster moonshine in the theory of the monster simple E group, the quantum field theory explanation for it is based on the same Feynman path integral that I'm about to tell you about, together with the conformal field theory constructed by Frankel, Lepowsky, and Merman. So in general, I'm about to tell you the aspect which Faddeev stressed in his in his lecture on the opening day, the aspect of quantum field theory ideas which is perhaps most indigestible mathematically, but which usually leads to the deepest results. So the heuristic motivation for this, well, we've made an association of Hilbert spaces with surfaces by picking a gauge group on a level K and quantizing. And this association is somewhat analogous to the association of a surface with its, let's say, complex cohomology, first cohomology. In each case, a diffeomorphism of surfaces induces some map on these spaces. And in the case of cohomology, if you pick a bounding 3-manifold, that actually determines a Lagrangian subspace in the first cohomology group, namely the subspace of things that extend over the 3-manifold. And you may ask whether there's some analog here. A surface is sitting there with its H1, but if you give a 3-manifold, suddenly that determines a subspace, a preferred subspace of H1. You can ask what's the analog here. And now, just for fun, let's guess what it might be. Of course, I'll make a slightly biased guess. If for every connection on sigma, we had a natural extension A prime over M. So we're given a 3-manifold sigma, and we're given a surface sigma, and we constructed a Hilbert space by quantizing the space of connections on sigma. And if for every connection on sigma, we knew how to extend it over M, so if every connection had a natural extension, then since an extended connection has a Chern-Simons invariant, not as a number but as a vector in some line, then if we had a natural extension of every connection, then we could define a natural section of this line bundle we've been talking about. Well, there's no natural way to extend connections. In fact, there isn't even a continuous and gauge invariant way to extend connections. But in what many regard as his greatest insight, Richard Feynman taught us more than 40 years ago what to do. Since there isn't a natural extension, we average over extensions. And every extension determines some vector in the corresponding line. So the average over connections is the vector in the line. And as the boundary data vary, so we consider for a given connection on the surface all its extensions. And averaging over extensions gives us a vector. And letting A vary, we get a section of that line bundle that I've told you about. And this is Feynman's recipe for computing transition amplitudes. Now, of course, I've made it sound like a possibly naive idea. There wasn't a natural extension, so we averaged over them, but a not very deep one. In Feynman's context, the problem a priori wasn't set up in such a way as to make that sound so much like the obvious thing to try. On the other hand, what Feynman was trying to do is similar to what we're trying to do in understanding the Jones polynomial. In those days, there was a theory called quantum electrodynamics that was really a 4-dimensional theory, but it was only formulated with 3-dimensional symmetry. Now, Feynman was trying to exhibit quantum electrodynamics in an obviously 4-dimensionally invariant fashion. Here we have a theory, the Jones polynomial and its generalizations, which is really a 3-dimensional theory, but the known formulations at most have 2-dimensional symmetry or even less in the original versions, and we're trying to exhibit it as a 3-dimensional theory. And we're simply following in Feynman's enormously successful and influential footsteps. Now, I'll in a bit try to make the notion that there is a way to average over this infinite dimensional space of extensions sound a little more palatable, but first let's indicate a few of the consequences. Well, first of all, if you believe you can average over connections, you can do it even on a three-manifold without boundary, or at least you can try to consider the case where the boundary is empty. So if we're given a closed three-manifold, well, we consider the space of all connections, or really connections modulo gauge transformations, on M, and we want to average over connections modulo gauge transformations. Or more conveniently, we usually average over all connections, including the Faddeev-Popov ghosts, to account for the volume of the gauge group. Anyway, we want to average over all connections, and now since we have a closed manifold, the Chern-Simons invariant is really a number, so the answer is a number, and it's a numerical invariant of the three-manifold. Now this is a very big integral, and maybe it's too big for one graduate student to do, but we might have two graduate students. So we split the problem into two pieces. We take what's called a Heegard splitting of the three-manifold. So we have a three-manifold X now, I've called it. I've regarded as a union of M and N. M and N are three manifolds with a common boundary with opposite orientation. So they fit together to make a nice three-manifold X. And we fix the boundary values of the connection on sigma. And we ask one student to integrate over extensions here, while the other student integrates over extensions here. And one student gets one functional of the boundary data, and of course the other student gets the other functional of the boundary data. And of course, if we fix the boundary data and integrate over all extensions, then we've integrated over everything except the values of the connection on sigma, and maybe the student's advisor, who should do at least part of the work, will then do the final integral over that. So the two students have constructed these two functionals of boundary data, and then perhaps the advisor integrates over the boundary data, and that final integral means that we finish the job and we have the invariant of this three-manifold, but we've obtained that invariant by pairing two pieces, one functional of boundary data obtained by one student and the other functional obtained by the other student. Now these two functionals were sections of our favorite line bundle. So what we found is that while each three-manifold determines a vector in this space, or the other one, because of opposite orientation, determines a vector in the dual, the pairing of the vector and the dual vector is our desired three-manifold invariant. And therefore we have learned that we are dealing with invariants that are computable from Heegard splittings, and more general considerations along these lines lead to a nice formula for the behavior under Dane surgery. So I haven't quite explicitly introduced knot invariants, but knot invariants are introduced similarly by considering a three-manifold with knots and considering holonomies of connections around those knots. And after formulating the problem for the knot invariants, then one can push a little farther on this formula by which we compute from Heegard splittings and get a formula for the behavior under Dane surgery. And that formula is really what makes the theory computable, because any two three-manifolds are related by Dane surgery. And for instance, if you want, you can use Dane surgery to reduce anything you want to know about any three-manifold to knots in S3, or in some ways it's even simpler to reduce them to braids in S2 times S1. Because if you get to the braids in S2 times S1, then you really have reduced this more general picture to the original Jones representations of the braid group, essentially, and their cousins for higher representations and groups. And so ultimately you get combinatorial formulas based on Dane surgery. And these formulas have been adopted as the definition in combinatorial approaches. Reshetykhin lectured on the work that Reshetykhin and Tureyev did to rigorously justify the combinatorial formula you get this way by checking the generators and relations of essentially Kirby calculus. in an elegant fashion that depends on the relations involving quantum groups. Of course, the tool that they used, the ingredients that come in doing so are the so-called quantum 6J symbols. And the quantum 6J symbols themselves have a natural representation in 3 dimensions in terms of these path integrals, which again is related to their essential properties. And is another side of what I mentioned earlier when I noticed that we were getting the Canisian examological equation, which one knows is related to quantum groups. So different ways of looking at this make different aspects of deriving quantum groups from quantum field theory. You see, I might remark that to physicists, quantum groups are rather funny things, because you might say that the name quantum makes it sound like physics, and perhaps it does, but what quantum is here being used in a rather loose sense. Quantum means that an algebra, in this sense, context, quantum is being used to mean that an algebra which is commutative or co-commutative is being deformed so that it doesn't have those properties anyway. But quantum mechanics is really a little bit more specific than just deforming commutative algebras to non-commutative algebras. Quantum mechanics really has to do with quantization of symplectic manifolds. The algebra which is being deformed is the algebra of functions on a symplectic manifold, and it's deformed to a non-commuting algebra of operators on Hilbert space. Quantum groups, as formulated so elegantly, involve the deformations of a Poisson manifold, but not of a symplectic manifold. And as such, they're really a bit outside the conventional framework for quantum mechanics and quantum field theory. If you wish to take the quantum group and reduce it to a more standard object, which is quantization of symplectic manifolds, or once a complex structure is picked, algebraic geometry, sections of line bundles over that moduli space M sub j, this much bigger story with the space of connections and the 3-dimensional quantum field theory puts the quantum group in a framework that really is quantum mechanics and quantum field theory. Of course, the drawback is that we're in a much bigger picture, which is less obviously computable. As so often happens in mathematics and physics, the more computable version, which is the quantum group, doesn't exhibit all the symmetries which are exhibited in the 3-dimensional story. One should think of this as one of many instances where there's a invariant definition, which is the definition involving quantum field theory on 3 manifolds, and there's a computable definition, a manifestly computable definition that doesn't manifestly have all the symmetries, which is the one that involves the reduction to quantum groups and the combinatorial approaches. Now, I think I should spend the last few minutes to give you a flavor of what path integrals are, and here I shall be following, as I should have said at the beginning, in the footsteps of Albert Schwartz, who considered the abelian version of this theory many years ago in the 70s, relating it to Reidemeister-Racing torsion. So, I want to say something which is mathematically precise about path integrals, though it doesn't give the complete story, and it's a challenge to give the complete story. So what I'll tell you is, if you give a physicist sight unseen a quantum field theory that was found behind a bush and has no particular redeeming virtues, I will tell you all that can be said about it, about path integrals based on general ideas. So the only general thing that you can say, in terms of really computing them, I mean. So, of course, even if you've reduced an integral to quadrature in finite dimensions, you usually can't compute it, and you look for some asymptotic expansions. And we will make an asymptotic expansion here, which is an expansion in powers of 1 over k. So the situation we're in is that we have a big infinite dimensional manifold, and we're integrating something. And the something we're integrating is the exponential of I times something else times k. So the prototype for this problem, I'm going to simplify it. So we really have the gauge group, and we should worry about the ghosts, the Faddeev Popov ghosts. But pretending they weren't there, the prototype is a finite dimensional manifold with a measure and a Morse function. It doesn't have to be a Morse function. In general, it's a larger class of functions. But let's think for simplicity of a smooth function with isolated critical points. And then we have a real number, and then we want to compute this integral. And of course, we can't compute it in closed form. We can prove it exists, but we can't compute it. But we can compute it in an asymptotic expansion in powers of 1 over t. And that's essentially classical. The asymptotics of such an integral is given by stationary phase. In fact, if f were not a function, but had values in r mod 2 pi z, and t was an integer, so there were no critical points, this would vanish exponentially for large t because of oscillations. So the failure to vanish exponentially due to oscillations comes because of critical points where there aren't oscillations. The asymptotics are given by stationary phase. If pi are the critical points, then this has a systematic expansion involving a sum over critical points where the leading term is the value of the integrand at the ith critical point times a power of t that depends on the dimension, and then multiplied by a local expansion determined by local data at the critical points. So these are, the coefficients here are local invariants at the ith critical point. And for instance, if near a given critical point you make an expansion, so I pick some local coordinates and I want them to be adapted to the measure so that d mu is dx1 up to dxn. And then since it's a critical point, the function has its value, and then the next term is a quadratic term involving the so-called Hessian. Then by studying the integral, the idealized integral, we find that the leading term is this animal, and that animal involves the determinant of the Hessian. Well, this thing has a determinant because of the existence of a measure here and the condition on the coordinates. So it involves the determinant of the Hessian and involves the signature of that quadratic form. So the leading contribution here involves these nice invariants of the behavior near the critical point. And then you can compute the higher order corrections involving local behavior near the critical points. You'll need to, the only new thing you'll really need is that you'll need to invert this invertible matrix. And then the expansion can be described diagrammatically in terms of what physicists call Feynman diagrams. Now, this can be imitated systematically in our problem. In fact, that's where they're called Feynman diagrams. Well, there's no problem with the notion of a critical point. Fuller explained that a critical point of this functional is a thought connection up to gauge transformation. And for a large class of 3 manifolds, they'll be isolated. In general, we need to understand how to generalize the previous story, which will involve certain integrals of measures that you'll construct. Well, what will happen, in fact, is that if the critical point isn't isolated, this determinant isn't a number, but is naturally a measure on the space of critical points. So after properly understanding the finite dimensional story, you can imitate it here. There's no problem with the notion of a critical point. There's, of course, no problem with the notion of the value of the Chern-Simons functional at a critical point. That's one of the standard invariants of a thought connection. Well, the Hessian makes sense after including the ghosts. The Hessian is a certain elliptic differential operator, which I'll call L. Well, then we need the determinant of L, but that's essentially what Ray and Singer defined and Schwartz interpreted in quantum field theory. So that the determinant of L is the Ray-Singer torsion. And then we also need the signature of L. Well, L is a quadratic form in infinite dimensions, so it has infinitely many positive and negative eigenvalues. So we need to define its signature, and we need to regularize that. But Tia, Patodi, and Singer told us how to do that in the so-called eta invariant. And in this problem, the eta invariant is the right notion of the signature of L. So I've explained the leading contribution for large K to this path integral. So we've actually, if you like, evaluated the path integral in the leading approximation of stationary phase. And It involves invariants that are classical, namely the more recent of them were defined in the early 70s, but they're still fairly sophisticated things like the torsion and the eta invariants. And the corrections, which are only beginning to be systematically investigated mathematically, involve what physicists call Feynman diagrams. My student Dror Bar-Natan has worked out rather precisely the two-loop correction to the non-invariants and has shown that it's equal to the, again, classical non-invariance, which is the derivative of the Jones polynomial at q equals 1, as was the second derivative, rather, as was expected. So then the story is that we can carry out the Hamiltonian picture more or less rigorously, getting the Jones representations and their generalizations. The deeper side of the story is certainly the Hamiltonian picture, which is a challenge perhaps to understand it comprehensively. In perturbation theory, it leads, in the leading approximation, to these classical but slightly subtle invariants with a systematic prescription for generalizing them and computing more elaborate corrections, perhaps rather as in some fashion which, in some perhaps rather fashion in the province primarily of experts. I certainly couldn't claim to grasp it. Bloch explained in the first lecture some generalizations of more classical invariants. Thank you.
Yes. Thank you very much, Professor Witten, and the informal seminar is finished. Thank you for attention.
Thank you.
What series printer reference?
Now the Professor Faddeev will speak on the work of Witten for Michael Attia.
It's a duty of the chairman of Fields Committee to ask speakers for that session. So as soon as it became clear that Witten got medal, I approached Attia, asking to speak for him. I wanted kind of cover up from a mathematician in the very theoretical domain to explain to you why it was so natural to give a Fields Medal to mathematical physicists. And Attia was very enthusiastic in this, but he told me that unfortunately he cannot come to Kyoto in the end of August. So we decided on the following way, that he will send me some text and I will use it in describing how Witten work at this session. So I had got this text and I will read you some excerpts out of it. But it contains no formulas at all. So just to read it maybe will be a little bit too dull. You have seen transparencies before. So in a way, it will be a mixture of Attia's text and some general comments which I will give to you myself, and some explanations. So mathematical physics must be considered as a legitimate, it's my belief, must be considered as a legitimate part of mathematics. It was always stimulating, it was always a source of stimulus and inspiration for more theoretical branches of mathematics. And we know very many classical examples. But until recent time, it was stimulating mostly analysis, or in general, or part of analysis, such like partial differential equations, especially nonlinear equations nowadays, and so on and so forth. We could call it classical mathematical physics. But in more recent time, we witness development another type of mathematical physics which could be in contradistinction with previous one, called quantum mathematical physics. And this mathematical physics differs mainly, also differs from classical mathematical physics in the use of different domains of mathematics in it, or in other words, also stimulating different parts of theoretical mathematics. Algebra, geometry, topology, algebraic geometry, complex analysis, all these traditional fields of mathematics now come to modern mathematical physics. And vice versa, mathematical physics, problems arising there in quantum mathematical physics are sources of new problems for this part of theoretical mathematics. And now I read first citation from Attia. In all this large and exciting field, which involves many of leading physicists and mathematicians in the world, Edward Witten stands out clearly as the most influential and dominating figure. Although he is definitely a physicist, here I would add mathematical physicist. His command of mathematics is rivaled by few mathematicians, and his ability to interpret physical ideas in mathematical form is quite unique. Time and again, he has surprised the mathematical community by brilliant application of physical insight, leading to new and deep mathematical theorems. Now, in Attia's text, there is elaboration on this general statement, and usually the reference is to an important tool of modern theoretical mathematical physics, which is called Feynman integral. Feynman integral allows us to write down explicit, in quotation marks, solution of very complicated problems arising in quantum field theory, quantum mechanics, and so on. Quotation marks means that this tool is still heuristic and not made rigorous to the standards which are supposed to be used now. They would certainly satisfy, I would think, more mathematicians in previous century, or even such people like Élie Cartan, but without more high standards of rigor, they are still non-rigorous, of course. On the other hand, as I'll try to explain with the help of Attia also, it's really a very important tool to find out new mathematical theorems. So the ingredient in the Feynman integral is a functional of some fields. Fields means functions on some manifold domain. So functions could be not necessarily functions, but sections of the bundle, and so on, so could have geometrical origin. And this functional is called action, and then functional x to the I, where I squared minus y times action is Feynman functional. And the Feynman integral is kind of averaging of this functional over all possible fields in consideration. It's symbolic as follows: that integral of a measure, of course, it's not measure in strict sense, is local, which is a product over all points in the domain or manifold of differentials of these fields, so to say. So the answer is a number, but of course, depending on what problem we have in consideration. For instance, we have a domain, the boundary, or we have some asymptotical conditions. Then, so there are some parameters which characterize the domain of this geometrical object we are averaging over. The function could be also functional of this data, and so quite a rich object. So the example, well, of course, physicists after Feynman, after 48, use it mostly for their own needs. And then functional A was action in the classical theory or classical mechanics of some particular Hamiltonian system. But in more general use, which gradually developed in this quantum mathematical physics, and especially by the influence of very modern things there, in particular what's called string theory, people began to use more geometrical objects in these actions and fields. So examples of possible fields could be loops or connections. It's called Young-Mills field in physics, or metrics. In physics, it would be most useful in the case of gravity, and so on and so forth. So Witten have shown a very ingenious way of using functional integral to produce purely mathematical theorems. Now I cite from Atiyah. In his paper on supersymmetry and Morse theory, Witten's paper on supersymmetry and Morse theory is obligatory reading for geometers interested in understanding modern quantum field theory. It also contains a brilliant proof of classical Morse inequalities relating critical points to homology. The main point is that homology is defined via Hodge harmonic forms. So the Laplacian will play a role of the Schrödinger operator of quantum mechanics, and you can write down Feynman integral using this action